Whatever aircraft you're flying, it's your responsibility to know both the limits of the pilot and the airplane. Because the Phantom is one of the most powerful, uncomplicated, and effortless airplanes to fly, even experienced pilots must develop a special understanding and feel for the F-4 and its flight characteristics. As an F-4 pilot, your objectives are to achieve maximum performance, to control the aircraft under conditions of high-angle attack, and perform all fighter maneuvers required in a combat situation. To accomplish these objectives, let's begin by studying certain handling characteristics of the F-4 during a normal takeoff. Normally, the Phantom will take off easier and a more comfortable attitude if you position the flaps at 1/2. To study that takeoff more carefully, let's watch it in slow motion. Start the stick back so that full aft stick is applied by 80 knots. As the aircraft starts to rotate, adjust the stick to maintain 10 to 12 degrees pitch attitude for aircraft fly-off. The basic takeoff attitude should be held during acceleration and transition to a clean configuration. When the aircraft is loaded with external stores, the takeoff is similar, with minor exceptions. All heavy gross takeoffs are made with afterburner. Variations in takeoff characteristics with stores are the result of combining factors of weight, pressure distribution, center of gravity, and inertial changes. During heavy gross weight takeoff, nose gear liftoff and takeoff speeds must be adjusted in accordance with aircraft gross weight. Forward center of gravity causes the nose to rotate later on takeoff. This is one of the primary differences to keep in mind, especially on short runways. When the Phantom reaches the desired takeoff attitude, the stick must be repositioned to bring the aircraft back into longitudinal balance to hold attitude. Get the stick back because 1 inch less than full aft stick means 10 knots greater speed before nose liftoff. A fully deflected stabilator will provide the necessary lift needed to rotate the nose. The nose will rotate at a rate proportional to the aircraft acceleration. The importance of gaining an adequate maneuvering margin shortly after takeoff cannot be overemphasized. During ground operation, the CG moves forward as fuel is consumed. When external fuel transfers, the CG moves aft as all fuselage tanks fill. When external tanks empty, the CG moves forward again as internal fuel is consumed. Remember, while the CG is aft, smooth control inputs are the key to good tracking and maneuvering. Over-controlling must be anticipated and carefully avoided. Because of this stability problem, you should always keep in mind the fuel sequencing of the aircraft and the adverse effects of an aft CG, especially during maximum performance maneuvers. If interpreted properly, the fuel quantity gauge can serve as an approximate CG indicator. For example, fuel in all tanks, including 5 and 6, indicates aft CG 8,000 pounds. Fuel in tanks 1, 2, 3, and 4 indicate mid-range CG, 5,500 pounds. And fuel in forward tanks, forward CG, 2,500 pounds. In order to maintain minimum longitudinal stability when carrying wing-mounted external stores, including tanks, the CG must be kept forward of 36% Mach. Refer to Handbook of Weight and Balance data for any given load. Developing complete confidence in your aircraft is essential to the success of any mission. A ground trim check with the ground crew will help build this confidence. It should begin during aircraft pre-flight and pre-taxi checks. If any out-of-trim condition exists, the aircraft commander should be informed, and a more thorough check of all controls accomplished en route to mission area and prior to any maximum performance maneuvering. Before practicing maximum performance turns or engaging in aerial combat tactics, the aircraft should be checked again in flight for rig and trim. During climb, with the stab auge engaged, trim the ball to center in the rear cockpit and check that the aircraft will fly wings level with ailerons trimmed to the neutral position. If a large amount of lateral trim is required to maintain wings level, an out-of-rig or malfunctioning stab auge exists. To isolate the source, perform the same check with stab auge disengaged. If the aircraft requires the same amount of lateral trim to hold wings level, the aircraft is out of rig. If not, a stab auge malfunction should be suspected. In either case, the aircraft should not be flown to maximum performance, as the handling characteristics will be degraded and loss of control may result. An angle of attack system is incorporated into the F-4 to present a visual indication of optimum aircraft flight conditions. Aircraft angle of attack is a function of airspeed, altitude, gross weight, and load factor. It varies directly with gross weight, load factor, and altitude, and inversely with airspeed. Angle of attack is one of the most important items affecting the stability and control characteristics of the F-4. The angle of attack indicator measures the angle of airflow in relation to the wings. It's a valuable aid during subsonic flight and presents the maneuvering margin available to the pilot, regardless of speed, G-forces, or gross weight. Successful confidence maneuvers rely heavily upon proper interpretation of the angle of attack. Confidence maneuvers reveal the characteristics of the aircraft and how the machine will respond if proper control and handling techniques are applied. It is during these maneuvers that you can explore unfamiliar areas of the flight envelope and discover how to enter, perform, and recover from low airspeed, high angle of attack conditions. The zoom climb confidence maneuver is performed by accelerating to a high energy level, then slowly rotating the aircraft to a pitch attitude greater than normal climb. Once you have selected maximum or military power and the pitch attitude is established, maintain this attitude until you reach the pre-briefed recovery airspeed. Should these maneuvers take you to altitudes of 50,000 feet or above, stabilator effectiveness will decrease and an increased amount of aft stick will be required to hold the desired pitch attitude. For recovery, you may use either of two maneuvers, a wings level or inverted recovery. In a wings level recovery, smoothly decrease angle of attack to a minimum positive G-force, 5 to 10 units, holding until the aircraft flies over the top and airspeed increases. In the inverted recovery, control angle of attack while rolling the aircraft inverted with rudder. Then increase angle of attack to produce a positive G-force condition. Both recoveries demand smooth control with minimum aileron. Avoid abrupt roll or pitch actions. Rolling the aircraft or changing the turn direction with rudder employs a principle called dihedral effect, or roll caused by side slip. Enter a rudder roll by establishing a 35 to 40 degree climb and allowing the airspeed to drop to 150 knots. As the aircraft is held in unaccelerated flight, with back stick and no aileron, smoothly apply rudder in either direction. The nose will start to drop, but continue rolling until nose is below the horizon and aircraft approaches wings level position. Then smoothly relax rudder pressure and counter with opposite rudder if necessary to regain wings level flight. Airspeed during maneuver will depend upon pitch angle at roll entry. The aileron roll is also entered by establishing a 35 to 40 degree climb and allowing the airspeed to drop to 150 knots. At this point, smoothly unload the aircraft and cross-check the angle of attack to obtain 5 to 10 units, and apply aileron in the desired direction of roll. As the roll progresses and the nose begins to drop, continue with control pressure, but keep the aircraft unloaded. The airspeed will approach 90 to 120 knots, depending on initial pitch attitude. As the roll nears completion, recover with neutral aileron and fly the aircraft out of low airspeed condition. The Phantom exhibits no well-defined classic stall characteristics. Specific characteristics will vary with aircraft rigging, loading, and control techniques. In an approach to a 1G stall, the F-4 will demonstrate a sequence of buffet buildup, roll and yaw oscillation, high sink rate, and deterioration of lateral control as angle of attack increases. Normal 1G stalls, with the landing gear retracted and 1/2 or full flaps extended, differ from 1G stalls in the clean configuration in that only very light buffet will occur until the stall develops. Prior to stall condition, the rudder pedal shaker activation at approximately 22.3 units angle of attack may be masked by heavy buffet and may be unacceptable as a warning device of the maneuvering limit. Study the 1G stall sequence again. Normal 1G stalls in the clean configuration are preceded by a wide band of buffet warning. Onset buffet occurs 40 knots above the stall and increases from moderate to heavy buffet immediately preceding the stall. The stall is usually characterized by a right yaw and a right roll, depending on aircraft rig. Recovery is easily affected by positioning the stick forward of neutral and reducing angle of attack while maintaining neutral ailerons and rudder. A different maneuver, an accelerated subsonic stall, demonstrates lateral instability in the form of wing rock, which occurs almost simultaneously with buffet, progressing to a fairly high frequency, large amplitude roll oscillation. Again, rudder pedal shaker may be completely masked by heavy buffet, and considerable yaw above 22 units may result, depending upon pilot technique. Rapid and abrupt control applications may result in a stall without noticeable warning from buffet and wing rock. To control this situation, promptly reposition the stabulator forward of neutral to effect recovery from accelerated stall entries. At subsonic speeds, if the stick is abruptly pulled full aft and held, a spin may develop, a spin that may not be broken within one turn. When flying the F-4 through maximum performance maneuvers, the techniques are basically the same as in other swept-wing Century Series aircraft. Normally, adverse yaw is induced while maneuvering at high angles of attack. Adverse yaw will produce a rolling moment opposite a turn direction because of the dihedral effect. The yaw opposite the turn direction finds its source in opposite deflected ailerons, lift vectors, and the tilted wings. Do not attempt to control adverse yaw by applying aileron in the desired direction of turn or roll, but keep the stick centered and use rudder to counter the tendency to roll out. At extreme angles of attack, adverse yaw can be of such magnitude that full rudder cannot counter it. Using improper control techniques to counter adverse yaw may result in a post-stall gyration or fully developed spin. A post-stall gyration is a tumbling motion about roll, pitch, and yaw axes. Aircraft motion will depend upon the speed and type of entry, and it's not predictable. If you counter immediately with recovery controls, the post-stall gyration will cease. Recover from this maneuver by holding the stick forward of neutral. Neutralize aileron and rudder, and maintain 5 to 10 units angle of attack. Maintain neutral controls for one full turn of yaw. If angle of attack is not below stall, deploy drag chute and maintain controls. A fully developed spin may occur from various entry conditions by use of improper or abrupt control techniques. For example, excessive aileron will produce a spin during slow speed, straight and level flight, vertical climb, accelerated turn, and accelerated turn reversal. The drag chute will help recovery from either an upright or inverted spin by producing the necessary nose-down movement needed to regain flying speed. Recovery from a spin, however, can usually be achieved by the correct application of flight controls. Stay in command of your Phantom. Don't spin in. It's an inglorious way to go. It must be emphasized that flying maximum performance maneuvers requires solid academic background, proper supervision, constant practice, and self-discipline. You'll need experience in all areas of the flight envelope. The knowledge and skill necessary to use the full capabilities of the F-4 weapons system comes from your air combat maneuvers training. Study your F-4, practice proper control techniques, and learn every possible thing you can about it. A thorough understanding of the F-4 flight characteristics will help you to become a successful F-4 fighter pilot.
The F-4 tactical fighter is a great weapon, and it demands great skill to fly it and fight with it. The F-4 fighter pilot can develop a high degree of proficiency in air-to-air gunnery using the dart target. The dart is mounted on a tow plane and towed through patterns that require realistic combat maneuvers of the F-4. The dart is released at altitude and towed on a 1,500-foot cable and follows the tow plane through the gunnery patterns. Firing must be done from the inside of the turn, but positioning for attack calls for a variety of left hand, right hand, diving, and climbing maneuvers. The common pattern used is the racetrack, with a climbing pass at one end and a diving pass at the other. Since this provides only left-hand or only right-hand turns, the racetrack has variants of figure 8 or figure S. The geometry of the range determines which is used. A later, more advanced pattern has evolved called the butterfly. It is not considered a replacement for the standard racetrack, but for more experienced personnel, it provides the closest approach to true aerial combat. After use, the dart is released over a designated recovery area to be picked up and checked for hits. Due to the relative small size of the dart to an aircraft, even a single hit is rated as a kill. A hit generally means good tracking, though a miss does not necessarily mean bad. Minimum harmonization standards require the M61 cannon to fire 80% of its rounds within an 8-mil cone. Cross sections of this cone give an 8-foot dispersal at 1,000-foot range, 16 feet at 2,000, and 20 feet at 2,500. Considering target size, this dispersal pattern can cause a miss at longer ranges, even with good tracking. The design parameters of the F-4's ASG-22 fire control system require that the attacking aircraft fly a lead pursuit curve with smooth and accurate tracking, and that it be flown coordinated. Over-controlling the rudder will shift bullet trajectory away from rudder applied. During any given firing pass, the pipper reacts to a variety of factors. If a pilot understands these factors, he'll become an expert. If he does not understand them, the pipper will lead him around by the nose. Take speed, for instance. The well-known floating pass is a condition in which a high closing rate, delta Mach, coupled with a low G condition, causes the pipper to slide ahead of the target, a difficult tracking situation. Range, too, affects pipper behavior. The closer to the target, the stiffer the pipper action. The farther out you track, the looser the pipper. Conclusion? Long-range putt shots are virtually useless. Because of the displacement between gun sight and the gun on the F-4, the center of projectile impact is indicated by the pipper only at harmonized range. However, from 1,600 feet out to the harmonized range of 2,250 feet, the pipper is very close to the center of projectile impact. A maximum error of 4 inches exists. Therefore, the pipper can be considered the center of projectile impact between 1,600 feet and 2,250 feet. An important point to remember is that while the gun sight computes much quicker than any pilot, its solutions are not instantaneous. It needs time. Time for radar input, time for gyro action and pickoff, time for computer solution. These reactions, added together, cause the pipper to lag slightly. You must allow for this. Take a simple yaw movement. The nose of the aircraft moves a split second before the pipper follows. On the return swing, the same lag occurs. No combat maneuver will be this simple, of course, but whatever the combination of forces, the principle remains the same. Allow the sight time to compute and the pipper time to react. Here's an actual case. The pipper is trailing the target, so the pilot applies back stick pressure to move the pipper up to the aiming point. This control input tells the computer that the target has, in effect, speeded up, so the computer starts to generate a larger lead requirement. The pilot should relax stick pressure to match target speed when the pipper is still slightly behind the aiming point. As the computer senses actual target speed, it will generate less lead, moving the pipper the rest of the way to the aiming point. If the pilot ignores the pipper lag, the pipper will slide ahead of the aiming point. Another difficult tracking situation. A final tip: look at the dart, not the pipper. Fly to your aiming point, which holds steady, not to your pipper with its loose, random movement. Target and pipper are close enough on the combining glass, you won't have to shift vision. Once you've placed the pipper where you want it, hold it there for about half a second to make sure that the system has finished computing. If you have established fairly steady tracking, open fire at around 2,000 feet. As a general rule, fire a short burst with the pipper on the target. Allow the pipper to settle on the target and fire again. Cease fire at 1,000 feet and break off by 800. You don't want to digest the dart or bring home a length of cable. Good shooting depends on more than pilot skill. It's necessary that your equipment be functioning properly. The pilot turns the radar mode selector switch to test and goes through the bit checks. The aircraft commander sets the sight mode selector switch from off to standby for 30 seconds. During this period, the reticle is not visible. After the 30-second warm-up period, the sight mode selector switch is turned from standby to cage. The reticle is now visible and in its caged position. The sight mode selector switch is then turned from cage to the air-to-ground position, then to the air-to-air position. Make sure the pipper is within plus or minus 2 mils of the cage position when the sight mode selector is switched from cage to air-to-ground and then air-to-air. Next, rotate the reticle depression control to the 10 mil position. The aircraft commander then moves his head to the right until the right half of the reticle display is obscured by the bit 1 mask. The aircraft commander sets the sight mode switch from the air-to-air position to bit 1. The reticle moves 25 mils in traverse until it is entirely visible except for the extreme right side of the display. The roll tabs rotate 90 degrees and the range bar slews to the 3 o'clock position, representing 4,000 feet. With the sight mode switch still at bit 1, the aircraft commander moves his head up until the upper half of the reticle is obscured by the bit 2 mask. The aircraft commander then sets the sight mode switch from bit 1 to bit 2. The reticle moves 25 mils in depression and becomes entirely visible except for the extreme top of the display. The roll tabs rotate 90 degrees back to the wings level position, and the range bar will slew to the 12:30 o'clock or 6,700 feet position. Next, turn the reticle depression knob to 35 mils and reset the sight mode switch to bit 1. The reticle display does not move. To cage the reticle display, set the sight mode switch from bit 1 to cage. The reticle returns to the cage position. At this point, it is caged for taxi and takeoff. The final pre-flight check involves the range bar. The pilot locks on to the first radar bit target. The range bar slews to the 1 o'clock position. That is the 6,000-foot range value. Should either bit 1 or bit 2 indicate a malfunction, an armament analyzer is used to determine the faulty unit in the lead computing optical sight system. When the flight leader calls for airborne sight checks, they are accomplished as follows. It is imperative that the station select button is not depressed while making the sight check. Number 1 and number 2 drop back in trail of number 3 and number 4. Number 3 and number 4 maintain a velocity of approximately 320 knots calibrated airspeed. The airborne sight check consists of identifying the target aircraft on the scope. Adjust the gain for optimum target return. Place the range gate over the target and go full action. An indication of lock-on is the appearance of the range bar in the reticle. As the target aircraft turns, the reticle depresses, indicating that the sight is computing the lead prediction angle. The power setting is then increased, and as the range begins to diminish, the range bar moves down. This indicates the optical sight is ranging correctly. When number 1 and 2 have completed their sight checks, they pass the other element on the outside and assume the lead so that number 3 and 4 accomplish their sight checks. With the airborne sight checks completed, number 1 makes contact with the tow ship. On completion of the contact, the flight proceeds to the preset orbit area. The tow usually orbits at 25,000 feet. If there are clouds, the tow ship must start the maneuver 10,000 feet below the cloud base so that attacking aircraft can stay in the clear throughout all maneuvers. Meanwhile, the tow pilot calls for range clearance. On their way to rendezvous, the attackers climb to arrive at the orbit area 2,000 feet above tow altitude. The racetrack pattern starts when the flight has entered the firing range and has visual contact with the dart. The firing aircraft should position himself approximately 1,000 to 3,000 feet above the target, 5,000 feet behind it, and offset no more than 15 degrees to either side. When straight and level on the home stretch, the tow pilot calls 30 seconds to turn. The attacker may initiate his pass any time after the 30-second call, depending on his perch position. If too far back, initiate the pass early. If too far forward, delay. Try to be level with the dart at 350 knots and about 3,000 feet out when the tow ship turns. The tow pilot calls 10 seconds to turn, then begins a 180-degree climbing turn. After he has established this turn, he calls cleared to fire. The attacking pilot must acknowledge this call by repeating it. The attacking pilot's wingman at this time should keep to the outside of the turn and high to avoid expended shell casings and pieces of the dart. The climbing turn is made at 0.75 Mach and 1.2 Gs, picking up 5,000 feet altitude with airspeed decreasing to 220 knots minimum. The tow pilot calls cease fire just before rollout. If the attacking pilot does not repeat this call, the tow craft will continue in a turn. Minimum attack speed is 300 knots. The tow craft rolls out straight and level, while the attacker maneuvers to get back on the perch. Because the tow ship turns away on the downhill pass, perch position should be closer, 1 to 3,000 feet above target and 3 to 4,000 feet behind. When the tow ship reaches 0.75 Mach, the pilot calls 10 seconds to turn, then goes into a diving turn. After the turn is established, he calls cleared to fire, which the attacker must repeat. The turn is maintained at 0.75 Mach and 2 Gs down through 5,000 feet, with a ceasefire call and acknowledgement before rollout. Minimum attack speed is 350 knots. One complete racetrack constitutes a series. Each attacking pilot flies 2 series. Rendezvous for the butterfly differs from the racetrack. In the butterfly, the tow craft and one of the attacking craft fly down the range in wing position at speeds of 0.75 Mach. When the tow pilot calls start separation turn, both aircraft turn away from each other and fly a heading 45 degrees from the original course. They maintain heading for 15 seconds. Then at the call, start second maneuver, roll in towards each other. This would be a collision course, except that while the tow pilot maintains speed and altitude, the attacker makes a climbing turn that puts him 3,000 feet above and 3,000 feet out from the tow craft. The attacker may change airspeed as desired after establishing the turn. As they approach line abreast, the tow pilot calls cleared to fire now. Now signaling the moment they pass. The attacker repeats, cleared to fire, and the target goes first into a 180-degree climbing turn into the attacker, gaining 5,000 feet altitude and losing speed to a 220 knot minimum. Then immediately into a diving turn, accelerating to 0.75 Mach and 2 Gs, back down to 25,000 feet. The attacker is free to maneuver and fire as he wishes until the tow pilot calls, "Cease fire," as he completes his first 360-degree maneuver. Reversing his turn, the tow pilot calls, "Cleared to fire." After repeating the call, the attacker is again on his own, free to maneuver and fire during the tow craft's climbing and diving turns, until the tow pilot once more orders, "Cease fire." In the butterfly pattern, the attacker has no airspeed limitation, but must not fire from the outside of the turn or head-on. When his firing series is completed, the attacker will call, "Sight caged, switches off," and make way for his wingman series. Extreme caution must be observed during the changeover, all elements calling position and maneuver throughout. For both the racetrack and butterfly patterns, various radar techniques are available to accomplish a lock-on. A basic radar setup is 1 bar, 10-mile range, and normal clutter. The pilot can search by varying his antenna elevation or by setting the elevation strobe at -2 degrees and requesting the aircraft commander to put the dart in the reticle under the pipper. After identifying both the dart and the tow plane, the pilot may switch from normal clutter to heavy clutter and place the range gate over the dart by starting at minimum range and advancing until the range gate reaches the dart. With this procedure, lock on and make sure that the range gate does not jump to the tow plane. A variation of the radar technique for locking on is the gyro out method. With the switch in gyro out position, the aircraft commander tells the rear seat pilot where the target is with reference to the wings of the aircraft. The radar heat switch is set at heat for this procedure. Once locked on, check the steering dot carefully to determine that it is in the center of the circle. If it is not, you are probably locked on to the tow plane. Brake lock and fire in the search ranging mode. Start bringing the pipper up toward the aiming point, but don't rush it. Small stick movement causes large reticle travel. If you over-control, you'll be chasing the pipper all over the sky. You can fire any time the tracking is steady enough to allow you to hold the pipper on target for about half a second. With 200 rounds loaded, you have enough ammunition for 4 half-second bursts. In cases where the airborne sight check has shown that you cannot maintain radar lock-on, you must use search ranging, which is computing continuously for 1,500-foot range. As you close in, position the pipper slightly behind the dart, then slowly move it up to rest on the target center. Range estimation is difficult. A handy cue to remember is that at 1,250 feet, the pipper is about half the vertical size of the target. As in radar lock-on, track the target for a half second before firing and fire half-second bursts. When all attackers have finished their series, they join up with the flight. Sights caged, switches off, and proceed to base. Expect mistakes. Gunnery, like flying, is an acquired art. It takes knowledge and practice, but these in turn bring success. The skills learned in dart training, combined with the aggressive maneuvering developed in the ACT program, will provide the tactical fighter pilot the tools necessary to destroy the enemy in air combat.